Okay, so if you don't remember, I've been sneaking that notation in. We've been using the like f prime and other stuff, but this is this notation, when you read it, we would say the derivative of y with respect to x. And we usually abbreviate that as just WRT as with respect to x. So if you're trying to make sense of what that is, that's, if we remember, we're always talking about rates of change here. So we're talking about the rate of change in y. Oops. In y with respect to x. So today what you're going to see is we're going to work on functions that aren't defined like y equals some form of x. We can still figure out how things are changing. And these are implicit functions. So basically, if we start when variables agree, what I mean is we're taking the derivative of x cubed with respect to x. So with respect to x, that's the world we've already been living in. It's just 3x squared. So there's not much change here. But what happens when you have the derivative of y cubed with respect to x? This is where it gets a little bit strange. So we have to use the chain rule to help us figure out what's going on here. The only way this is possible is that there is some way that they are related. Like maybe, I don't know, maybe y is equal to cosine of x. There has to be a connection in order to work together, right? But when we're working implicitly this way, what we're going to say is this is going to be 3y squared times the derivative of y with respect to x. So maybe, like I said, this was that missing piece, the derivative of y with respect to x, and we could substitute everything back in and work it out. But for now, we don't know what that is. That's not in our problem. We can't use that or rely on that. We just have to leave it in as a means of accounting. So what I mean to try and help you wrap your head around that is, this would be the derivative if the variables agreed, this 3y squared. But because it doesn't agree, there must be some function that relates them. And so that's like the chain rule, a function inside this. And that would be related to x. So this is the function of y's derivative times how y is related to x. Okay? It's pretty simple when you do the derivative. You can't forget that part of it, though. It's not always there. Like, you look at this and you think, oh yeah, no problem. That's 1 plus 3. So close. What's missing here? Yeah, because it's 3 times the derivative of y with respect to x. I don't yet know how the two are connected, so I just have to keep it in my problem whenever I come across variables that don't agree. This one, again, is going to be a product rule. So if I did it with product rule, it would be the derivative of the first times the second plus the first times the derivative of the second, which is 2y dy dx. So I could rewrite this as y squared, oops, plus 2xy dy dx. So here's the guidelines that I'll give you then for doing implicit differentiation. And the only part that's really new here is don't forget dy dx when they don't agree. Okay. Then what we're going to do is move all the dy dx's to one side. That way we can factor them out. And then finally all we have to do is solve for dy dx. At this point, I just want to jump right into an example so you can see it's not that scary. Here is a function that's defined implicitly. And there is a connection between x and y. It's given to us in this equation. However, it's very hard to do it explicitly. It's hard to come up with a y equals form of this. So we're just going to pretend that it is there, and we're going to go through this implicit differentiation to find it. So let me show you. It's going to be, the first piece is 3y squared dy dx. Then the second piece would be 2y dy dx, and minus 5 dy dx, and sorry, there's one more piece, minus 2x equals to 0. So this is, everybody just got the derivative taken on all those pieces. And remember, I have to account for there's a relationship somehow between x and y, but it's way too hard to find it explicitly, so I just keep it there in my problem. So that's step number 1 that we just did, if you're keeping track. So step number 2 is we need a way to solve. So I'm going to suggest that you move everything to one side and factor. So it would look like this. I would go 3y squared dy dx plus 2y dy dx minus 5 dy dx is equal to 2x. I'm going to sound like a crazy person when you listen to this. 3y squared dy dx plus 2y dy dx. Just, does that not sound crazy? Yeah? Okay. It's not just me then. So all I've done is, by moving them to one side, it's easy to factor out. If you look, there's dy dx on each piece. So here, here, and here, and I'll factor them out. So I'm going to get dy dx, and the pieces are 3y squared plus 2y minus 5 equals 2x. So the only thing now is to solve it, and if I want to solve it then, dy dx will be 2x divided by 3y squared plus 2y minus 5. Okay. That's the derivative given implicitly. Now notice the derivative now has y's in it. The reason it has some y's in it is because there's y's in the one we started with up top. That's okay, but it means now if you want to know the derivative from me, I can only do it if you give me the points. I can't just do it from an x value. I need to know an x and a y. So let's try and find them at these points here. So I'll call this one number 1. We'll work on that one first. So 2 times 0, well, this is not going to be very interesting. It's going to knock the rest of the fraction out right there. But I'll plug them in just to show you the way. I need to move over where there's more room here. That was correct. Let's put it in here. So for number 1, if I put in this point, the derivative is going to be 2 times 0 over 3 times negative 3 squared plus 2 times negative 3 minus 5, which, well, I don't know if it's fortunate or unfortunate, but 2 times 0 is 0, so it doesn't really matter what's on the bottom. The rest of this fraction is still going to be a 0. So this will be, let's see here, 27 minus 6 minus 5, so 27 minus 11, which is 16. So it's just 0. And if we were to try it with this other point, 2, 0, I love it when they give zeros. Makes a lot less work. Just makes my day. Negative 4 over 5 would be the derivative here. So again, it's always a good idea to stop yourself and make a picture to see what's happening. This is the only one I know of. Maybe some of you with those fancy TI billion-and-one, whatever version you have now, can do this. But this graphing, it's a free one, and it does a nice job of implicit functions. So let's take a look at what we just did, try and make some sense out of it. Ooh, what would you call that? A beaker? A weird? All right, fine. the points that we looked at was 0, -3. So x equals 0, y equals -3. That's this one right here. You can visually see now what that slope is, right? That slope is 0. Flat line. So let me try here. That would be the tangent line that we put into it at 0. So let me remove that one. Then the other slope that we had was at x equals 2 and y equals 0. That's right where the crosshairs are here. And it told us it was -4/5. So that means the tangent line that would go through this one point here would be -4/5 if we were to do it. So sloping down a little less than 1. So even though we don't have an explicit function, it's still not that bad to find the derivative. Okay, so let me show you an example here of why you want to know how to do implicit, other than the fact that, like, I don't know how they dreamed this up, but that would be quite difficult to work on explicitly. Here's an ellipse. That means oval. I'll just show you the picture first. Ellipses are easy to define implicitly. X squared plus 4y squared equals 4. So there's my ellipse. We're going to take this derivative implicitly. Here's the version that you'd have to work with otherwise, right? This one here. You already have a chain rule to work on because of that square root and the x squared. But implicitly, I can find a derivative here if I know this technique. So you try it and see what you come up with for the derivative of that ellipse. There, let's walk through this together then. Those variables would agree, so it would just be 2x, then 8y times dy dx equals to 0. And that means I'm going to get 8y dy dx is -2x. So it's pretty, to solve, all I have to do is divide. So dy thank you, yeah, dx is -2x over 8y. And we should cut that down at least to -x over 4y. So this again is the derivative of y with respect to x. It's good to say it in your head when you see it so that you remember what you're doing. This is the rate of change in y with respect to x. You don't need to do this because we have the technique. It is possible, however, to do it explicitly. But I'll leave that up to you if you feel like doing the harder form of it. But this is the derivative you'll end up with. Oh, sorry, by the way, it's slightly different. The derivative you're going to end up with, because y equals that, that means you won't have a y in your derivative. You'll have a monster that looks like this. Oops, sorry. You'll have this piece in its place, right? Let me move these over. You'd have something in here like this. -4 and negative. Got those. Because this piece here is equal to y in explicit form. So there's nothing to stop you from, hey, let's do it the derivative implicitly, then throw back in the value of y. Now I would have an explicit derivative here, even though I did it implicitly to start. Okay, but anyways, just I guess sort of a not really interesting fact, but something you can do. Okay, so your turn here. Get some efficiencies at it. Those next three, see how you do. Again, it's also going to test your skills on chain, product, and other stuff you've done, but this time implicitly. So for this first one here, I'm going to have the derivative of the first piece, which is 2x times the second. And now the other one gets a turn. So the derivative here is just going to be 1. However, that's the derivative of y with respect to x. The variables do not agree. I will need to keep this in here. So this here, if I put some red brackets around them, that corresponds with my red circle there. That's all I've done so far. Okay, then the next one, the derivative of the first piece will be 2y, but the variables don't match. I'm looking for the derivative with respect to x. And now this second piece, it'll be y squared times the derivative of x with respect to x. So it's fine. It's just going to be 1. And that will be equal to 0. So my strategy was then to factor out. So I'm going to have x squared dy dx plus 2xy dy dx equals negative 2xy minus y squared. So if I factor out, negative 3 became 0 when I took the derivative. So this gives me a derivative then that looks like this. Okay, we're going to go to the next one. This next one here is a chain rule start, so it'll be 2 times x plus y to the 1. Now I need the derivative of the inside piece, which is going to be 1 plus the derivative of y with respect to x. Now what I've got is something I'm probably going to want to expand if I hope to solve this for dy dx. So that means I'm going to have 2x plus 2y, 1 plus dy dx. And then I'll expand it again, so I have 2x plus 2x dy dx plus 2y plus 2y dy dx. We'll rearrange this equation. Dy dx is going to be factored out with 2x plus 2y. Those are the two pieces on it. And negative 2x minus 2y on this side. So since I'm running out of space there, I'll divide it out here. So it'll be 2x plus 2y. And that would be gone. Now, can anybody see anything interesting about that one? Yeah, it's just going to be negative 1 once it simplifies. So as strange as that is, it means everywhere on that it's negative 1. So we should hope that this simplifies just to being the line y equals negative x then, right? Same derivative, something like that anyway. Okay, and then finally, this one here, this is a chain product, meaning there's a chain rule and then a product rule inside it because I have e to the xy. So it's going to look like this. The derivative of the outside is my favorite. It's just e to the xy. But now I have to take care of the derivative of the inside, which is 1 times y plus x dy dx. 2x, and I'm going to run out of space here, minus 2y dy dx equals 0. Made it, kind of. So my strategy is I need to get all the dy dx's to one side, so it'll look like this. Y e to the xy plus x e to the xy dy dx plus 2x minus 2y dy dx is 0. So I'm going to move these pieces here, leave them on that side, move the other ones to the other side. So it'll look like this once I've factored them out. Make it a little smaller here, dy dx. And the first piece is x e to the xy minus 2y. And it'll be negative 2x minus y e to the xy on the other side. So that finally leaves me with, let's see here, negative 2x minus y e to the xy over x e to the xy minus 2y. Wow. Thrilling, isn't it? So those represent like the not so practical version of implicit differentiation, meaning that there's a lot of stuff happening in there, a lot of algebra. For the most part, things like these polynomials are convenient. That's probably the world we'll live in. But it's not to say that you're off the hook, because as we said, this course is cumulative. Everything we've been doing keeps following you. So we'll take a look now at higher order derivatives. It's exactly as you knew it before, but there is one slight trick to it. So let's step through this first one together to see what I'm talking about. Anybody know what this equation looks like? It is, yeah, it's a circle with radius 5. Don't worry if you didn't know it, but it is what a circle of radius 5 looks like. So let's take the derivative. Okay, so the derivative should go like that, and hopefully you're at the point where you're comfortable with what I've just done. Now we have to do it again. So it's going to be a quotient rule this time, and let's work on that quotient rule. If you don't know this notation here, those 2's mean the second derivative of y with respect to x. So we'll be doing the second derivative is going to be quotient rule -1 times y minus -x dy dx. And on the bottom, it'll be y squared. So the problem this time is that that we're in the second derivative and the first derivative hung around. But actually it's not that bad, because what I'm going to do is take that first derivative that's still part of my, my rough work, and I'm just going to substitute it. Here it is. So it would look like this. Second derivative is -y plus x times -x over y. Just put it in there where we had it before. And now I'll just tidy up a little bit. I've got that fraction, so I'll multiply everybody by y over y. That'll knock out all my complex fractions. So -y squared minus x squared over y cubed. So to find the second derivative, I had to use the first derivative, and that's a common task that you will be faced with. So as you see it the second time, that means you need to go back to where you found it the first time. And just for those of you that love algebra, this is kind of an interesting the way this turns out. If we do a couple more steps here, that's a pretty simple second derivative. It's kind of strange. Actually, x isn't even involved anymore. How did I get rid of the x and y squared? With 25, but how did I know that? Yeah, I used the first one up here. So that's clever. That's not something that is expected, but that's clever. Now if I had to take another derivative, there's no more x's to deal with, just y's. Now, for the sake of time, I am going to go on to this last one. That means we'll have to just put an unhappy face or maybe a happy face beside the next one, okay? If you do want to practice that one and talk to me about it, I'll stick around, but otherwise, log differentiation is the, again, it's something that's going to be kind of a giveaway when you see it, because otherwise the problem looks much too hard. So like this here, all kinds of chain rules, quotient rules, and everything like that. what we can do is, provided that this is greater than 0, we can take its logarithm, right? Because this would be the equation I end up with. Which is still valid, provided that I don't give it any negative numbers to mess up the logs. And now, why would I want to do that, you're probably asking yourself. Well, do you remember what happens when we do this with the exponents and the quotient rules and product rules? Yeah, log laws help us a lot. So this will be the natural log of x minus 2 squared minus the natural log of x squared plus 1 to the 1/2. So I can call that 2 natural log x minus 2. And now I don't actually need to deal with those exponents anymore, right? So I'll end up with 2 over x minus 2. And 1/2 1 over x squared plus 1 times 2x. There's still a chain rule I can't get rid of with log laws there. So let me tidy it up a bit. And what did I have here? So those 2's are gone. Minus x over x squared plus 1. Okay, now this would be wonderful if that's all we had to do. But notice over here, that's what the natural log is. It's not the actual derivative. So here's, all we have to do then to fix it is, if that's what the natural log of y, let's say, this guy here, then we have, yeah, stop it. This guy. So all I had to do was use our implicit differentiation to get back to y and get out of the logarithm. So I said the derivative of that thing is what we just found. So 1 over y dy dx is that. And again, like you've already been doing, we'll just move the y over. So that means I have dy dx is y times 2 over x minus 2, like that. And since they gave it to us in explicit form, we can even take that equation and go like this. And now I have the explicit derivative, but oh my, did I ever not have to do all those chain rules, product rules, and awful things that would have happened if I didn't use the logarithm to do it. So can you imagine getting this derivative without having to do it? It would be pretty terrible. So not that it wasn't terrible on its own, but hopefully less so.